Hi, and welcome to a video on evaluating the unit circle. All right, so throughout this lesson, we are going to have the unit circle up and present. If you don't know how to create the unit circle, then check out my other videos. I have a video that shows you how to create this thing from scratch. But for now, I want to say that on this unit circle, we have an infinite number of points. Okay, the only reason why we have these particular points labeled is probably because number one, we use these angles quite often in the real world 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. Those come up pretty much all the time while we're building things. But also, we can evaluate, based on those angles, we can evaluate their XY coordinates without a calculator, which is what we're going to do today. All right, so let's go ahead and bring up a small little illustration just to remind ourselves that with any one of these reference angles, we can create a right triangle. And the amount we travel in the x along that right triangle, which is the length of this side, happens to correspond to the x value of the coordinate. And the amount we go up or down in the y, right, for that triangle, that length of that side, corresponds to the y value of this coordinate as well. Okay, so what we're going to do is we're going to bring up our 6 trig functions. And we're going to use probably our basic SOHCAHTOA at first, but then we're going to extend that just a little bit. So SOHCAHTOA basically tells you how to define, or it tells you the definition of the sine of an angle, the cosine, and then the tangent. But we're also interested in all of their inverses, which I've got these paired up. The cosecant, which is the inverse of the sine, which basically means that the cosecant of theta is equal to 1 over the sine of theta. Okay, that's what it means to be an inverse, and vice versa, by the way. All right, but either way, also we have cosine paired with our secant, and we have tangent paired with our cotangent. So let's go ahead and we're going to say, well, instead of using, like in SOHCAHTOA, sine of theta is equal to opposite over hypotenuse, we're going to actually fill in these values based on our unit circle over here. Okay. So the sine of theta for this particular triangle right here, and actually I shouldn't say this particular, this is the same. It would be the same for any triangle that existed inside of this unit circle. But anyway, the sine is the opposite. So we're going to go opposite of theta, which is y, divided by the hypotenuse. And the hypotenuse for every one of these right triangles is going to be 1. So in this case, the sine of theta is equal to y divided by 1. So I'm just going to write that instead of y over 1, I'm going to write it as just y. And now we're going to go ahead and do the same thing with cosine. The cosine in SOHCAHTOA is the CAH is the adjacent side over the hypotenuse, or x over 1, or just x. And actually, what you just did there was show why any one of these points. You can pick any point. Like, let's pick this point right here, right? This point corresponds to cosine of theta as its x and the sine of theta as its y, right? And we just showed that. Okay, so now we're going to go ahead and we're going to define the rest of these, because we're not just interested in the sine and cosine. That's good to know, but we do want to know some of these other ones, the evaluation of some of these other ones as well. So the tangent in SOHCAHTOA is opposite over adjacent. So in that case, the opposite is the y over x. So I will write that as y divided by x. And I'm actually going to also define that because as the trig function, because y is the same thing as sine of theta. So that would be the same thing as sine of theta divided by x, which is the cosine of theta. Sometimes it can be really handy to know both of these relationships. All right, now, since the cosecant is the inverse of the sine, or 1 over the sine, that is the same as 1 over y. And the same thing for secant as an inverse of cosine, which is 1 over x. And then cotangent is the inverse of tangent, and so we're going to flip these, the y and the x, so you get x over y. Or you could write it as cosine of theta divided by the sine of theta. Now, we're going to evaluate these, but I want to show you really quickly like like why are these actually important? You guys can see that the sine is the it has a length, right? It is the measure of a length of this some kind of value, right? And it's the length of this triangle over here, and the x also has it's a measure of the horizontal length of that triangle. But what about tangent and cosecant and secant and cotangent? Well, real quick, let's just go check that out. So I'm going to bring this up. And this is a little graph in Desmos. And I want to show you here that the red, so we're interested in this point right here as it moves around. Okay, whoops, don't want to move it that way. But as it moves around. And so the cosine happens to be this red value, right? That is the same as us traveling down here in that same length. The sine is the height here, so this blue one. Now, what is the tangent? The tangent is actually the length of this black one right here. The cotangent is the length of this green one right here, this green segment. The secant is the length of this orange one, and the cosecant is the length of this purple one. And just to set this thing going real quick, you can see that, yeah, these relationships, like these are related to each other for sure, right? As some get bigger, others get smaller, which are showing those inverse relationships, okay? Anyway, and you can kind of see as, how they change as they go around that unit circle, okay? All right, so what we're going to do is we're going to go back now, and let's actually evaluate some of these. Okay. All right. So let's come up with an example here. Let's see. We're just going to kind of pick a few of these. So let's do it down here in our free space. So I'm going to say example number 1. And let's do an easy one first. And actually, let me turn off my turn that off and we'll go back here. All right, so anyways, let's do an easy one. Let's do the sine of let's say, I don't know, 135 degrees. All right, so what does that evaluate to? Well, I'm going to start at my initial side as always, 0 degrees, and I'm going to go around to 135 degrees, and that is this guy right here. Right, and you could, of course, draw in your triangle if you want, right? But we actually don't need any of that. All we really need to know, if we already know the values in our unit circle, is the x and y, which correspond to the cosine and the sine. And so we know that the y happens to be the sine, right? And we showed that up here as well. So in this case, the sine of 135 degrees is the y value of the square root 2 over 2. And there you go, all done. Let's go to another one. Call this example 2. And let's go the same direction. We're going to go a positive way, which is counterclockwise, but we're going to wrap around more than once this time. Let's make it a little bit more challenging. Let's do like a tangent here. So I'm going to say the tangent, and let's do 405 degrees. So this is more than 360. So what does this evaluate to? So I'm going to start at my initial side, go counterclockwise. And I'm going to go all the way around 180 degrees, 270 degrees, 360 degrees, and then 405 is another 45 degrees. So here we go. We end at this 45 degree terminal side, which again, you can draw on your triangle if you want, but all I'm really interested in are the x and y values because I can evaluate any other one of these other trig functions with just those. But anyway, so the tangent is the y over the x. All right, so that is the square root of 2 divided by 2 for the y, and the x happens to be the same in this case, square root of 2 over 2. And so when I have two things that are the same being divisible by each other, then that is just equal to 1. Okay, so the tangent of 405 degrees is 1. Which, by the way, you literally just measured the length of this little segment going off this way, this little tangent segment going off there. So the length of that it happens to be 1. Kind of interesting, the same as the radius. All right, let's do another one. Let's see here. So example 3. And this time, let's go the opposite direction. Let's pick a different one. Let's do the secant, and we're going to go the opposite direction. Let's do like negative 135 degrees. All right, so I'm going to start at my initial side and go the opposite way. So negative 45, negative 90, negative 135 would be right here. So 90 plus another 45 degrees. So that gets you at this 225 right here. And so I'm interested in this point, these coordinates. And so the secant is the inverse of the cosine, right? So if I know the cosine, I could just flip it. And a lot of times that's the quicker way to go. Let me just show you what that is. So the cosine, which is the x value, is negative root 2 over 2. If I flipped it, that would be negative 2 over root 2. And then I'd have to rationalize. But I'm going to show you the whole way. So going off of secant, that is 1 over x. So 1 divided by whatever the x value is, which is negative root 2 over 2. And when I divide by a fraction, it's the same thing as multiplying by its reciprocal. So I'm going to say this is equal to 1 times negative 2 over root 2. I'm just going to leave the negative in the top because I like negatives in the top, not on the bottom. So I'm going to now, well, 1 times that is just negative 2 over root 2. And now I'm going to rationalize this. We don't like to have radicals in our denominators, so I'm going to multiply top and bottom by the square root of 2. And let's bring this down here. So this is equal to, I have negative 2 times the square root of 2 on the top. And on the bottom, I've got root 2 times root 2, which is root 4. And the square root of 4 is 2. So that's 2. And now these 2's are going to cancel, giving us negative square root of 2 over 1, or just negative square root of 2. And so we can say that the secant of 135 degrees is negative root 2. Exactly. Right, and that corresponds to a real measurement, as we showed in our in that nice little animation. That's a pretty cool animation. Let's bring it up again, right? So where is the secant? It's the orange line here would be this secant. So the purple one is the cosecant. So anyway, kind of interesting. So all right, let's get back to it. We're going to do 2 more problems here and wrap it up, just because we haven't done anything in radians yet. And so it's good to practice your radians because, people are not familiar with radians, mostly because they don't practice them. So let's go ahead and do a few. So this is going to be example 4. And for this one, let's do the cotangent. We haven't done that one yet. And we're going to do... Let's just pick one here. Let's do 5 pi over 6. All right. So first things first, 5 pi over 6. Where in the world is that? Well, I'm going to start on my initial side. I'm going to go around until I hit my 5 pi over 6 angle right here. And so I'm interested in this guy right here, this terminal side. And so here we go. Here's my x and my y. Now the cotangent is the inverse of tangent, right? Tangent is y over x. Cotangent is x over y. So I'm just going to go ahead and go straight to that. So x over y is negative root 3 over 2 for the x, divided by the y of 1/2. And again, when I divide by a fraction, it's the same as multiplying by its reciprocal. So this is the same thing as negative root 3 over 2 times 2 over 1. And when I multiply these 2's are going to cancel, getting you negative root 3 over 1, or just negative root 3. So if I wanted to figure out what the cotangent of 5 pi over 6 was, what that actual measurement was, it's negative root 3. Okay? All right, let's go. Oh, and by the way, you might be interested in the fact that, yeah, some of these do have negatives. Yeah, because it corresponds to actual coordinates, right? It is also measuring the lengths, and lengths usually are never negative, right? You would never say the length of something is negative. That doesn't exist. But since this is actually being mapped to an xy coordinate plane, you can actually tell where that exists with those negatives. Okay? All right, let's do one more. And this will be example 5. Last one here. And we're going to do another radian one. Which function did we not do yet? I don't think we did a cosecant. So we'll do a cosecant, and let's do, like, I don't know. Let's do a negative radian, and let's do negative 11 pi over 6. Kind of hard, but not that hard. All right. it would be harder if we went wrapped around more than once, right? But anyway, in this case, it's just a little bit harder because it's negative. That's it. So first of all, if it was positive 11 pi over 6, I would start here and then go to this guy, right? But this is the negative version of that. So I am going to start at the same spot and then go negative wrapping around 11 pi over 6, which gets you right here. So it's the same thing as actually 30 degrees, right? Not very hard. And cosecant is the inverse of sine. So the sine is 1/2 in this case. And I know that if it's the inverse, I just have to flip it around. So instead of 1 over 2, it's 2 over 1 or just 2. So the cosecant of negative 11 pi over 6 happens to be 2. All right, so there you go, you guys. There's a lesson on how to evaluate different angles on the unit circle. And also, I hope that you saw that, yeah, these measurements of these 6 trig functions, they actually do mean something. They do measure different lengths depending on, whether they're like tangent segments or right triangles or whatever, based on this unit circle. And also, furthermore, I don't know if you guys really, if you've never seen this before, but this is another little tidbit. You don't have to do this with just the unit circle. If you could do this with any circle. The only real difference with any circle is that instead of x being the cosine of theta, it is r, the radius, times the cosine of theta. And instead of y being the sine of theta, it is the radius, or r, times the sine of theta. So yeah, actually you could apply this to pretty much any circle at that point in time. All right, guys, I hope you enjoyed this lesson, and I'll see you in the next one.